Hi, my name is Lukas, and today I will present the Shared Task submission of the BCAI, the Bosch Center for Artificial Intelligence. This is joint work with my supervisors Heike and Yannick. In the MEDDOPROF Shared Task, we participate as the NLNDE team, neither language nor domain experts, and we participate in the first two subtracks only. And I assume, similar to most participants, we solve both tasks by modeling them as sequence labeling problems. Given the huge popularity of pre-trained transformer models, we also follow this trend and use the multilingual XLM-R model as the foundation for all of our models. Building up on this, we experiment with several upgrades to improve the model. This includes, first, the domain-adapted pre-training of the transformer model to steer it towards this special Spanish clinical domain. We experiment with model transfer between the two tasks because they are highly related. We also experiment with training using strategic data splits as an alternative to random splits. And finally, we also test ensembling of multiple models. All of these topics will be discussed in more detail in the following. Let's start with the actual sequence tagging model. As we are using a pre-trained transformer, there is no direct need to apply an external tokenizer to the data. Thus, we use the subword tokenizer that comes with the transformer model, and we perform sequence labeling on this subword level. For this, we split each document into sequences of 300 subtokens, and then we add the surrounding context of 100 subtokens to the left and 100 to the right to capture a wider document context. This input sequence is then processed by the transformer model. In our case, we use the XLM-R model. This is a multilingual language model, and it was pre-trained on a large-scale corpus covering about 100 languages. The predictions for each subtoken in the sequence are then produced by a conditional random field output layer. We have chosen this over a simple linear layer to cope with the long annotations of the shared task. In addition, a CRF can help to avoid inconsistencies in the label encoding. And as label encoding, we have chosen the BioSE encoding, and this has additionally separate labels for the ending of an annotation and a special markup for single word annotation. And this XLM-R CRF model here we see is the foundation for all other experiments, and we use it similarly across all runs. And now I will continue with the potential extensions, and starting with a closer look at the XLM-R model itself. In particular, we have chosen this model as it was pre-trained on a giant corpus of multilingual text, and of course Spanish data is in there as well. In first experiments, we observed that this model outperforms the multilingual BERT by a large margin, and it is also better than monolingual models. However, we also see that the Spanish pre-training was only a small fraction of the overall training, even though the Spanish subcorpus is quite large with more than 50 GB. That's not even 2% of the whole thing. In order to steer this model more towards the special domain of Spanish clinical text, we continue the masked language modeling on Spanish data. So for this, we first tried training on a general domain Spanish corpus with data from various domains, and second, we tried only Spanish text from the clinical domain. This, of course, results in a much smaller corpus, but it's more relevant to the text style of the shared task. And by looking at the numbers, we can observe that the language model fine-tuning has a very positive impact on performance for both tasks. We get a 1-point improvement for the first task and up to 3.6 for the second task. And in addition, we now have 3 different transformer models for our experiments that we can use and compare to: the original one and the 2 adapted Spanish models. But how can we further improve now? Well, we tried transfer learning. As both tasks of the competition are highly related, they even have the same annotation boundaries. We wondered whether the information learned for one task can be beneficial for the other task. For example, if the model already knows which token belongs to an annotation, shouldn't it be easier to classify the corresponding person in the second task? For this, we performed model transfer by first training the model on the first task. We call this our auxiliary task. Then we transfer this model to the new task, our main task. And we do this by initializing the sequence tagger with the learned weights from the first task. After this, we can perform just normal model training. And we can actually do this for both tasks. So first training task 1, then task 2, and vice versa. Our results indicate that transfer from the first task to the second task is beneficial and it improves performance by almost 3 points. This indicates that the training to detect job expression helps to classify them later on. However, the same does not hold the other way around. That leads to our next improvement. As there was no official split into a training and development set for this shared task, we wondered how we should perform early stopping and model selection. Instead of creating random splits, we took all the available data for training, and then we stopped according to the training loss. While in principle this works fine and has the advantage that the model sees the most data during training, the loss is not as meaningful as the stopping criterion as the score on a development set. Thus, we also tested with a separate development set for early stopping. And again, we don't want to use random splits. Thus, we decided to create more interesting data splits, so-called strategic splits. In short, the corpus is splitted into clusters of similar documents. That means if one cluster is left out for validation, very similar documents are not part of the training, and this can give further insights into the generalization ability of the model. To create the splits, we represent each document by an embedding vector that is retrieved from the XLM-R model, and we do this by averaging over all the token vectors. Then we apply PCA to reduce the dimensionality, and based on these we cluster the corpus using k-means. So now that we have split the corpus into 5 clusters by the similarity, we train on 4 of these splits and leave out one split as our validation set. And we can leave out every split once. This results in 5 different models per setting. No one can argue that each of these models has not seen an important part of the corpus. And while this is true, there are 4 models that were trained on this split. To combine the knowledge of these slightly different models into one, we used Ensembling. This helps to capture the advantages of the different models by creating a combined prediction. For this work, we use Ensembling by majority voting. In particular, we use so-called hard voting that creates an ensemble of the predicted labels by choosing the highest voted one. For our submission, we test 2 different approaches. First, we can combine the 5 models trained on the strategic data splits, but we can also combine the different transformer models, or we can actually do both. Here are some numbers. So we can see that the Spanish XLM-R, which already improved upon the standard model, can be further boosted with ensembles over strategic data splits, and this increases performance by 2 to 3 F1 points for both tasks. Now let me show you some more results. These are our submissions to the shared task, and the first one is the fine-tuned XLM-R on the clinical domain. We see that the results are pretty good with 79 and 77 F1, but as you have seen earlier, we will improve upon this with the next submissions and extensions. The second submission was an ensemble over all 3 transformer models, and this includes the first one as well. It was performing a lot better than the single model for the first task, but it was not as good on the second task, as the standard XLM-R model has far below performance of 74 F1, and this just leads to a drop in performance. The third submission was the test with model transfer. Again, we have the ensembles of all 3 transformers, and we see that's improving the performance for the second task. The fourth submission was our best model. Here we make an ensemble over the 3 embeddings, and for each we use the 5 models trained on strategic data split. This improves the performance of the first task to 81.1, our best score for this, and it improves the second task by almost 2 points to 79.3. Our last submission was just an ensemble of all models. This is slightly worse than the submission before, but comparable. There is just too much noise in there from inferior models. One more thing we noticed after the deadline was that the fine-tuned Spanish XLM-R over strategic data splits without the other 2 embeddings is by far the best model for task 1. This reaches an F-score of 83.2. Okay, these were our submissions, and you have also seen the system for the MEDDOPROF Shared Task. We have seen how each of the extensions can lead to great improvements of already high-performing transformers, and in particular, the strategic data splits are very promising and an interesting future research direction. If you want to run this model yourself, you can follow the link or scan the code. Thank you for listening and goodbye.